Today we're going to prove the mean value theorem for integrals. If f of x is continuous on the closed interval ab, then there is at least one c in the open interval ab such that f of the c value is equal to the average height, basically that's saying. In terms of a diagram, what this is saying, let this be the x-axis, and maybe this is A, so let's label it, and this is B. So the area, the integral, is giving us the area between these two blue lines, A to B, and the curve f of t, or since I labeled it axis x, how about f of x? Now, the mean value theorem for integrals is saying that there's a special c value. We'll say such that f of c is that height. And what it's saying is that the area of this rectangle, the area of that rectangle is equal to the area of the integral. And the area of that rectangle is this height right here, is f of c. Then the area of the rectangle is clearly the base times the height. And that's supposed to equal the area from A to B of f of t dt. And all we're doing is we're dividing both sides by b minus a. So that's what's going on. Let us derive this or prove this theorem. So proof. Since f of x is continuous on the closed interval AB, there must exist a C1 and C2, both in the closed interval, such that f for C1 is equal to the minimum of f of x on AB, and 2, f for C2 is equal to the max of f of x on the closed interval AB. Now, what we have is, so let's say this, it is clear that f for C1, which is the min, but let me just write this on another line. I need more space. Let's say f of C1 times the base. This is going to be less than the integral from A to B of f for t dt, which in turn is going to be less than f for C2 times b minus ba times b minus a. So what we have is this. This is in the middle. I don't care what this is. It's a real number. Integral or not, it's a real number. And it is in between here and here. Now, let's just make one more comment. Since f of x is continuous, so is f of x times b minus a. And it is continuous on AB. That is, this function is continuous. I'm just evaluating it at C1, which is in the interval AB, and C2. So what we have is that this is a continuous function. We have that this is less than that, and this is smack in the middle. So by the mean value theorem, there must be a C value that is going to satisfy what we want. And I will show you what we want. Now by the mean value theorem, there has to exist a C. Well, let's say by the mean value theorem applied to f of x times b minus a. When we apply the mean value theorem there, we have our C in C1, C2. We have our C in between C1, C2, which by the way is in AB. Maybe I don't make the equal sign, but it wouldn't matter. So there's the C in between AB such that f for C times b minus a is going to equal that number. Is going to equal to that number, regardless of what that number is. And that number is an integral. Oh well, a definite integral. So we did find the C in AB such that this equals that. Now before I say I'm done, just want to see what I said. We are going to show that f for C equals that. So coming down here, I'm just going to divide both sides by b minus a. Then f for C is 1 over b minus a times the integral from a to b of f for t dt for some c in equal to interval a to b. A to b. And that's what we set out to show. The proof is now done. If you like proofs like these, or leave a comment. If you don't like proofs like these, leave a comment. Most of all, leave a comment in the comment section. If you have any proofs that you like for me to show, leave a comment and there's a good chance I'll show your proof on my YouTube channel. Thanks for viewing. Remember, watch and learn.